This is section 1.5. We're going to talk about the notion of continuity. So we say a function f of x is continuous at x equals a if the limit as x goes to a of f of x is just f of a. And I want you to think for a minute and recognize that this looks an awful lot like the direct substitution property that we talked about in the last section, and in fact it is. So what it's really saying, if you want to, we can say i.e. f has the direct substitution property at x equals a. So what it means is this limit, the y value that f of x is getting closer and closer and closer to as x gets closer and closer to a, that y value is f of a itself. It need not be in general, but when these two y values agree, then we say that the function f is continuous at the specific x value. And so I want to highlight the sort of three things that fall out of this definition. So if f is continuous at x equals a, then you know that this relationship holds, and that's really telling you three things. So here we go. So the first thing it's telling you is that f is defined at a. A has to be in the domain of f. F of a has to make sense. If there is no f of a, then you certainly can't have this limit equal to f of a, right? So certainly f has to be defined at a. Okay, the second thing that it's telling you, whoops, how do I slide this down? Oh boy, here we go. Second thing it's telling you is that the limit as x goes to a of f of x, this limit need not exist in general. It might simply not exist, but if you know that the function is continuous at a, then you know that this limit actually exists. There is a number that f is getting closer and closer to as x goes to a. And finally, you don't just know that it exists, you actually know the specific value of the limit. And so just make sure that you're aware that this final statement really encapsulates these previous two statements as well. Okay, so let's do an example, and we'll list out all the x values where this function g is not continuous. Discontinuous just means not continuous. And so why don't you pause the video and think about that yourself for a minute. And maybe when you say where a discontinuity is, go ahead and say why as well. All right, so let's start with x equals 1 right here. Here's x equals 1. This function is not continuous at x equals 1 because the function isn't defined there. There's a hole there. So x equals 1 is a discontinuity. Let's say is a, we'll say is a point of discontinuity. And we can say since g of 1 is undefined. All right, so that's our first one. The second point that we'll think about is right here at x equals 2. And think about it, the limit from the left is whatever this y value is down here. This is the value of the limit. The limit from the right is 2. And so since the limit from the left is not the same as the limit from the right, you know that the limit doesn't exist. So x equals 2 is, let's copy this, is a point of discontinuity. Let's see if we can do that. Is a point of discontinuity since the limit as x goes to 2 of g of x simply does not exist. Okay, so that's a problem. So there's a problem here, there's a problem there. And then finally, let's look out here at x equals 1, 2, 3, 4. What's up with 4? Well, here the function is defined. G of 4 is this value. G of 4 is 2. The limit exists. The limit as x goes to 4 is this y value of 1. But the limit and the value of the function are not equal. So we can say x equals 4 is a point of discontinuity since the limit as x goes to 4 of g of x is not equal to the value of g of 4. And I'll go ahead and write down the values. This limit is actually equal to 1, whereas the value of the function is actually equal to 2. So, okay. Well, let's stop this video here, and then I want to talk about continuity on an interval in the next video.